Hello everyone and welcome back. Today we will be talking about fluids and I will be doing it in a more organized manner. That is, up till now in this channel I've just been doing things randomly. That is, I've taken topics from over here and there and I've just made seemingly not connected videos. I mean, they were just things that I found interesting and I thought that I should discuss them. But beginning from now, I'll be trying to do a more formal and a more organized manner of creating videos. At least I hope so. So I'll be beginning with fluids. There's no special reason as to why I've chosen to begin with fluids. I just thought it was a relatively a short topic to cover. So let's formally begin, I guess. So this over here is a liquid or a fluid that has been kept at rest. Now, when fluids are kept at rest, there is something very special that can be said about the force that they exert. And that special thing is the fact that the force that they exert is always perpendicular to the surface. Right? So this over here is a perpendicular. And so we can say that the net force that this fluid exerts, it's perpendicular to the surface. And we know that, and the reason as to that is quite simple. Imagine that an object was kept on this fluid. Now, if the force was not perpendicular to the surface, then the fluid would exert a force, say, somewhat in this direction, right? Okay, that does not look very good. Hold on. Suppose the fluid exerts a force in this direction, right? So the object will also exert a force back on it according to Newton's third law. And thus, there would be a component of that force along the horizontal, which would cause the fluid to move. But we know that the fluid is at rest. So, if a fluid is at rest, the force is always perpendicular to the surface of the fluid. So now let's talk about pressure. Now pressure, as many of you might know, is simply force, that a force exerted by some object or entity on something divided by the area that is being exerted on. Or if you're dealing with really small areas, we could say that the pressure is the limit of as this area tends to 0 divided by limit of this area tends to 0, the same expression, but we're talking about really small areas over here. Suppose if you wanted to just find the area of force exerted on this very small part of the fluid. So using this definition of the pressure, Pascal actually formulated a very famous sort of law, and he said that the pressure exerted by a fluid at the same horizontal level is equal, and this follows no matter what the arrangement of fluid particles is above the surface of the fluid or below the surface of the fluid, no matter what the shape of the container is. Suppose if I had a container of this shape, alright, so the pressure at, say, this horizontal level, this would be equal. Pressure at this horizontal level, this would also be equal, and so on and so forth. So basically this holds true no matter what. So, well, let's look at a proof of that. Alright, so for the purposes of the proof, we are going to consider a triangular prism within the container. Alright, now this is not actually a solid prism that has been made of glass or something like that. This is only a hypothetical shape. That is, we are only considering a volume within the fluid, right? So this is the front face of the prism, and now I'm going to sort of draw it backwards as well. And so this is the entire prism. I'm going to call the face in the front, so let that be A, B, C, that's supposed to be B. And let the face of the back be D, there's a point back there, I'm going to call it E. And this is going to be F. Alright. And though this prism seems really big, I'm going to ask you to assume that this prism is actually very small within the fluid, and that the variation of height with respect to this prism is virtually negligible. And so we are assuming this so that we can in fact prove our statement, that is, the pressure at the same horizontal level is the same. That is, I'm going to ask you to assume AB is basically very close to 0. Alright, so we just saw that if there is a pressure exerted on this portion of the fluid, it's going to be perpendicular to the surface. So knowing that, what I'm going to do is I'm going to call a force, say F, that acts below the surface of the fluid. Suppose you have the fluid right below this, right? That is the bottom face of the prism, that is the face BEFC. Okay, I'm going to call that force just BC. Okay, now there's also a force that is acting, and there's another force acting on face ATPE, that is the side that we know, that is perpendicular to the surface of the container, if you can imagine that. So that is force F. I'm just going to call it AB. Alright, and then there's a force acting on this face over here, and that force is actually equal to, say, F A, let's just call it AC. Alright, and of course there are also forces acting on faces A, B, C, and faces D, E, F, but we're not counting them because they are most likely equal in magnitude and opposite each other, so they'll cancel each other out. So since we have three forces and we know that the fluid is at rest, so every particle has to be at rest. So as a result, we can conclude that the vector sum of these forces over here, remember that these forces are actually vectors, the vector sum of these forces will actually be equal to 0. Alright, and we let this angle be, say, theta over here. So I can draw a triangle that contains these forces, suppose, say, FAC, and we can, this is in fact true because these forces are in equilibrium, and if three forces are in an equilibrium, then we can always represent them in the form of a triangle like this. Okay, so this is like this, and I'll just extend this a bit over here. So this over here is a BC, that is FBC, and FAB, and FBC. Alright, and it turns out this over here is actually the same angle theta. Alright, so suppose if you wanted to find the area of this face, so suppose if you just wanted to find the length of BC, right? Let's not talk about area at the moment. Suppose you want to find the length of BC, that would actually be equal to AC cos theta, right? So let me just write that over here. You can write BC is equal to AC cos theta, and you can also say that AB over here is equal to AC sin theta, right? And we can also say that the corresponding areas are simply these sides multiplied by the width, suppose say an arbitrary width of the triangular prism that you've considered here. We're going to let that say be T. Okay, so we can say ABC is equal to AAC, that is, we're talking about the areas right now. All I've done over here is just multiplied the expression by T, and over here as well. So we can say AAC cos theta, and we can say AAB is equal to AAC sin theta. And now you'll finally see why I went to so much trouble of doing this. Since this is the same angle theta over here, what we can say is we can have exactly the same relation, and this will actually be FBC is sin theta is equal to FAB, and F, this is supposed to be FAC, I think. I mean F, oh my bad, oh god. This was actually FAC, right? This is actually FAC. So this is supposed to be FAC as well over here. My apologies. So this is supposed to be FAC sin theta is equal to FAB. We're talking about the magnitudes over here. And AC cos theta is equal to FBC. Now if we divide, see if I number them equations, and if we just divide, we'll find that Suppose say I number them 1, I number them 2, I number them 3, and if I number this 4, and suppose I do say 1 by 4, and so that will actually be FAC by AAC, and then also the cos thetas, but I've cut them, is equal to FBC by APC. And similarly, if you divide say 2 by 3, you'll find that the same expression, and so we can also say F AB by AAB. And what do you think this expression over here is? This is nothing but the pressure that is exerted on each of the surfaces or the faces of the fluid or the prism that we've talked about over here. So we can simply write PAC is equal to PBC is equal to PAB. And since these are all pressures that have been exerted at approximately the same level, that is the same horizontal level, we can then conclude that the pressure exerted by a fluid at any horizontal level is in fact equal in magnitude, and thus they have proved Pascal's law. However, there is something to note over here, and if you had been listening carefully, you might have probably caught on to that too. That is, as to why exactly have you assumed that the angle theta of the prism over here is the same as the angle theta in the case of the forces, and to some extent you can rationalize that by the fact that the force that is exerted is most likely proportional to the areas that is over here. But if we do assume that, it turns out we're already assuming the fact that the pressure is equal, because if we assume that force is directly proportional to area, then the pressure of the fluid that the fluid exerts is the proportionality constant. So in a sense, this is not really a proof because you're already assuming this. So, and kind of makes sense because the Pascal's law is a law that is observed from nature. It is an experimental law. So it's sort of like the gravitation law or the electrostatic law. There's not really a proof of it because they have been observed from nature. So I guess that's something to think about in your spare time. So with that, we move on to the next topic of sorts, that is the variation of pressure with height. Now we saw what happens at the same horizontal level, but what if we want to compare two pressures at different horizontal levels in the same fluid, right? At different heights. So for that also we have a very convenient expression. In this case, we'll again only be considering a fluid at rest. We'll be talking about fluids in motion later when we talk about Bernoulli's theorem. So over here as well, we're going to talk about pressure. Say over here again, we have considered a cube. You can take any arbitrary shape. Again, it really doesn't matter. For convenience sake and for easy explanation, I've just assumed it as a cube. So we know that there's a pressure exerted on all of these faces due to the fluid. But here I'm only going to mention two forces in particular. That is the force on the top and the force on the bottom. All right, because the forces on all the other four faces will be equal in magnitude and they'll be cancelled out naturally. So I'm going to call this force, say, force A, right? And I'm going to call this force, say, B. Now there's something that can be said about these two forces, right? In this case, we can't simply equal them because there is in fact some water that is present within this cuboidal or cubical region. In the previous case, we had assumed that the height was virtually negligible, so we also neglected the amount of, say, water or the fluid in general that was kept in this cubical region. But in this case, we simply cannot do that. So what we can say is that since the fluid is still in rest, we can say that the force B over here supports not only the force exerted by this force A, but it also supports the weight of the fluid within this region over here. So what we can write is FB is equal to, let's say that there's a mass M within that region, plus FA. Alright, so if we divide this thing or the entire expression by area, we'll get an expression in terms of pressure, and that is PB is equal to mg by A plus PB. So now you might be thinking that the mass m actually depends upon the shape that we choose, and hence it is dependent on that. But what we're going to do now is we're going to express mass in terms of density and volume. So we can say mass is equal to rho into the volume of this cubical region. Now that can simply be written as, say, now if this was suppose the height h, right, we can say the volume of the cube is actually h cube. Or in general, you can simply say rho a into h, where a can be the arbitrary cross section of the uh, shape, and h is the difference in the heights, or the height difference between these 2 points. So we can say m is equal to rho into volume, and I've written v is equal to a into h. So pb can now be written as rho a h g by a. If we cut the a plus a and we write this, apologies, I have to write b over there. So if I write pb over here, oh my god, I've written pb in both places, my bad. Say pa and pa, we can say the difference in pressure between any 2 points separated by a height h is actually equal to rho g h, and this again is a very important principle. And if you'll see, suppose if the height difference is zero or is negligible in the above case, you'll find that the two pressures are actually equal. And so this can be thought of as an extension to the Pascal's law. That is, not only is the pressure at the same height equal, but also the difference on pressure between any 2 points depends only on the height difference between the 2 points. So I think that will be it for this video. In the next video, we'll be dealing with Archimedes principle and the equation of continuity. So keep an eye out for that, I guess. And thank you for watching.